Welcome to lecture number 36 on this NPTEL course on fluid mechanics for undergraduate students in chemical engineering. Today we are going to discuss applications of fluid mechanics to various chemical engineering processes, and one of the major topics in chemical engineering applications is the flow of particulates in fluids. In many chemical engineering applications, for example, you have a system like a channel in which you have many particles that are settling in a liquid, okay, and these are called settling tanks. Okay. So, here particles are moving and settling in a fluid, okay, due to gravity, and this is used to separate particles of different sizes because of their difference in settling velocities, as we will see. So, this is one example. There are settling tanks or sedimentation tanks, as they are called in many chemical engineering applications. You will have sedimentation tanks that are used to remove particulates from one liquid phase, and then you use the liquid phase for further processing in other unit operations. And you also have centrifuges to separate particles of different densities, okay, particles or droplets of different densities. So, here the driving force, here again it is settling, but under the influence of centrifugal driving forces, and you have other unit operations such as packed beds, wherein you have a bed of particles, okay, which are in close contact, and there is a lot of gap in between the particles and fluid is flowing, okay. Fluid is flowing in the interstitial gap between these particles, and there are also other applications such as fluidized beds, wherein you have the motion of fluids through a bed of particles, but the particles themselves are no longer static, but they are also in some sense fluidized or suspended. So, they are also in a state of animated motion due to the fact that the drag force exerted by the fluid on the particles exceeds the weight of the particles. So, the bed of particles starts fluidizing after some velocity. So, all these are examples of motion of particles in a fluid, okay. And in order to design these operations well in many chemical engineering operations, unit operations, you have to understand the fundamental mechanics of flow of particulates through a liquid, okay. So, one of the simplest problem that we will first start with is flow or motion of a single particle in a fluid. In a fluid, okay. So, essentially we will imagine that you have a spherical particle, rigid particle to begin with, of some radius or diameter d, okay, and that is moving with a constant velocity, okay, under the influence of gravity, let us say, and we want to be able to predict what is the settling velocity of this particle as a function of various parameters in the problem, okay. Now, we already know that the drag force experienced by a sphere is correlated in terms of non-dimensional groups C d as a function of Reynolds number, where C d is nothing but 2 F d, the force, divided by maximum projected area times rho V p squared by 2, okay, and then Reynolds number is of course defined as d p V p rho by mu, where d p and V p are the diameter and velocity of the particles. F d is the drag force experienced by the particle. So, C d is nothing but 2 F d by pi r p squared rho V p squared, okay. Now, if I substitute for Reynolds number small compared to 1, the drag force is given by the Stokes drag law 6 pi Rp eta Vp. So, CD is given by 2 times 6 pi Rp eta Vp, okay, divided by pi Rp squared rho Vp squared. Okay. So, CD for a spherical particle at low Reynolds numbers is given by, so 2 times 6 is 12, and then the pi cancels off, 1 Vp will cancel with 1 Vp and Rp will cancel with 1 Rp to give you 12 by 12 times eta by rho Rp Vp, but Rp is dP by 2. So, CD is 12 times eta 2 by rho dP Vp, and this quantity is the Reynolds number of based on the particle diameter and velocity. So, the drag coefficient is given by 24 by divided by Re based on the particle for Reynolds number of the based on the particle much small compared to 1. Of course, at higher Reynolds numbers we showed that you have log CD versus log Re plot, and it will appear like this. For smaller Reynolds numbers it is a constant, it is a straight line with slope -1, okay. But at higher Reynolds numbers of course things are different, and you will find that, okay, there is a region of constant, relatively constant drag coefficient, and then at a Reynolds number of about 10 to the 5, this is about 10, you have transition from laminar flow to turbulence. Okay. So, we have this data, this is an experimental observation correlated in terms of drag coefficient and Reynolds number, experimental data. Okay. So, now we want to worry about settling velocity of a sphere. Imagine you have an infinite expanse of fluid, and then you take a sphere, okay, and you drop it, okay, in the fluid, in the liquid, and there is gravity. Okay. After some time, let us say you drop it with 0 velocity, initially the velocity of the sphere is 0. After some time, initially the sphere will accelerate, okay, because there is acceleration due to gravity acting on it, but it is also being retarded by the fluid drag force. Okay. This is the gravity force, let us call it Fg, okay, the gravity force that acts, and then there is drag force that acts in the opposite direction. There is also buoyancy force that acts in the opposite direction. Okay. So, these are the 3 forces. Now, initially there will be an imbalance if you write force balance for the particle. So, the mass times rate of change of velocity, acceleration of the particle is sum of all the forces. So, let us assume a coordinate frame x, y and z. Okay. So, the velocity, okay, mass times dV by dt is sum of all forces, and the gravity force is in, okay, let us simply write the algebraic quantities of all the algebraic, so let's use a sign convention. The gravity is Fg is acting is minus mg, okay. F buoyancy is plus the volume of the sphere. Let us assume the diameter of the sphere to be some d. Okay. So, the buoyancy will act in the plus y direction, because it is in the buoyancy acts in this direction, the direction opposite to the motion of the particle. Okay. So, buoyancy will act in the plus direction, which is rho pi dp cube by 6 times g, this is plus. Then there is drag force which is given by, okay, it is also in the plus y direction. So, the drag coefficient is defined in the following way. Okay, let us look at the definition of the drag coefficient here. From here we can back out a drag force which is nothing but pi Rp squared rho Vp squared by 2. Now, if you write Rp as dP divided by 2, okay, then Fd will be simply pi by 8 rho Vp squared dP squared times Cd, of course, times Cd. So, I will write Fd, the drag force, in terms of the drag coefficient. So, the drag force is pi by 8 times rho Vp squared dP squared times the drag coefficient Cd. So, at steady state you will have no when the sphere has reached a terminal, when a sphere has reached a velocity such that all the forces balance, its acceleration is 0. So, this is called the terminal regime, wherein the sphere velocity does not change with time, the velocity of the sphere is constant, that is independent of time. Okay. So, you have to simply balance all the 3 forces, okay, and the 3 forces are simply 0 is minus rho p pi dP cube g by 6. This is the weight, rho p is the density of the particle times the volume of the particle times g is the weight of the particle, it acts in the minus y direction, times rho times pi dP cube g divided by 6 plus pi by 8 rho Vp squared dP squared times Cd. Okay. So, if I eliminate for Vp, okay, we will get Vp is equal to square root of, if I solve for this equation for Vp, you will get 4 divided by 3 times rho p minus rho divided by rho dP g divided by the drag coefficient. So, this is the terminal steady terminal velocity of a sphere. Okay. Expression for terminal settling velocity, okay, of settling of a sphere of diameter dP, which is moving on density rho p, which is moving in a fluid of density rho. Okay. Now, of course, we have to look at different regimes. When Reynolds number is small compared to 1, we know that Cd is 24 divided by Reynolds number based on particle diameter. Okay. So, Vp becomes 4 by 3 times rho p minus rho divided by rho, okay, times dP g by 24 Reynolds number to the power half. Okay. So, Vp is nothing but, or we can square the entire expression, Vp squared is nothing but, okay, we will get, okay, so you have 4 6, so you get 18 here, so you have 1 over 18 rho p minus rho divided by rho, okay, times dPg times, you have to substitute for Reynolds number. Reynolds number is dP fluid density rho Vp divided by eta. Okay. Now, this fluid density will cancel with this density, one factor of Vp will cancel with one factor of Vp here to give you Vp is nothing but rho p minus rho dP squared times g divided by 18 eta. So, for low Reynolds numbers, the settling velocity is given by this expression. So, notice that the settling velocity for low Reynolds numbers is proportional to square of dP, the particle diameter. Okay, that is a key. If everything remains constant, okay, if you just worry about the variation of the settling velocity on the particle diameter, it goes as the square of the particle diameter. Now, let us look at high Reynolds numbers. Now, I told you that when Reynolds number is in between 1000 and twice 10 to the 5, there is a region of constant drag coefficient. Okay, if you look at this data, here Cd is approximately constant. So, we are looking at this regime where Cd is approximately constant, it is a number, okay, and that number is approximately 0.44. So, then we have to merely substitute 0.44 in this expression for Cd, okay, and then we will get an expression for the settling velocity, and the settling velocity for this regime is approximately 3 dP g rho p minus rho divided by rho to the power half. Now, notice here that this is the settling velocity at the relatively higher Reynolds number regime between 10 to the 3 and twice 10 to the 5, 10 to the 3 and 10 to the 5. Okay. Notice that the settling velocity is proportional to the diameter of the particle to the power half. Okay. So, there is a square root here also. So, the way in which the settling velocity depends on the diameter of the sphere is very different whether the Reynolds number is small or large. Okay. It goes as settling velocity goes as diameter of the particle squared at low Reynolds numbers, while it goes as diameter of the particle to the half at high Reynolds numbers. Okay. Now, this expression can be used to measure the viscosity of a fluid, and such a device is called the falling ball viscometer. Okay. Essentially, the idea is you drop a sphere in a fluid and wait for it, you take a sphere and place it in a liquid whose viscosity you want to find, okay, and wait for it to attain terminal velocity. Calculate the velocity by noting how much distance it travels over a particular time t, and that will give you the terminal velocity, settling velocity. So, the settling terminal velocity is measured, okay, in the experiment by simply measuring the time the particle takes to move a certain distance, and from there we can calculate the viscosity of the liquid in which it is settling through other parameters. Okay. So, divided by, okay. So, merely inverting this expression. So, if the Reynolds number is low, so we can pull eta here and then Vp here, that is all we have done in this expression, and you get an expression for viscosity provided you know what is the diameter, density of particle, density of fluid, and you measure the settling velocity, okay, velocity of settling of the particle. So, this is often used to measure the viscosity in many industrial settings, because it is easy first of all to do such an experiment, and this is assuming that the Reynolds number is small, because you choose your particle dimensions such that the Reynolds number based on the particle is very, very small. Now, in the above, when we use the Stokes drag law, okay, this is the Stokes drag law valid at small values of particle Reynolds number. Okay. When we use the Stokes drag law, we are assuming that the fluid is infinite in expanse. That is, there are no surrounding walls, but in reality there will be a surrounding wall. Suppose you may do an experiment in a container, okay, and therefore, you have the diameter of the particle d and then the diameter of the container, let us say dc. Okay. In principle, you may expect that when the diameter of the particle is very small compared to the diameter of the cylinder in which it is flowing, it is moving, then you would assume that the wall effects on the drag law is negligible, because this drag law is valid only if the walls are infinitely away from the particle, but in reality that is not the case, because we do experiments often in a laboratory where there are confining walls of the cylinder or whichever container we are doing the experiments. But you can also correct for that. So, the drag coefficient is 24 by Re times some function of dP by dC, where people have found using experiments what this functional form is. Okay. So, initially it goes as 1 plus, okay, it goes 1 plus this function is what I am plotting as a function of dP over dC. Initially it goes as 1 plus 2.1 times dP by dC. So, when dP equals dC, of course, we expect the function to go to 1, and then it starts deviating. Okay. So, the confining walls tend to increase the drag, okay, because there are additional dissipation in the problem compared to when you have no confining walls. So, typically when dP by dC is less than 1 over 20, then the isolated sphere results is isolated sphere result is pretty good, answer is pretty good. Okay. But when the confining walls are when dP by dC is such that it is not as small, then you will start seeing the effects of the confining wall, and that is given by this correction. Okay. So, we have seen what is meant by settling of a sphere, okay, and we are going to now first understand that it is not just that drag coefficients are defined only for spheres. You can have in many applications particles of other shapes also. So, a general definition of drag coefficient is simply CD is the drag force divided by half rho Vp squared times AP, where AP is the projection of the solid object on a plane normal to the direction of flow. Area of projection of the solid object in the direction normal to flow. Okay. So, for example, if you have a cylinder that is moving settling, suppose you have a cylinder settling like this and you have a cylinder settling like this under the influence of gravity, the projected area here is very different. Okay. Here the projected area is simply it is going to appear like a rectangle. Here the projected area is going to appear like a circle of radius pi dP squared by 4, or okay, whereas here the projected area is pi dP times L. Okay. So, it is very different depending on, sorry, not there is no pi here, just dP times L, because it is going to appear like a rectangle, okay, of dimensions dP times L. Okay. So, the drag coefficient is defined differently because the projected area is very different. Okay. And similar drag laws, I mean, that is how the drag coefficient depends on Reynolds number is empirically found using experiments for other geometries such as cylinders as well, but those are matters of experimental detail which can be found in textbooks, or those are just just empirical data which can be found in textbooks. But the idea is you do have similar drag coefficient versus Reynolds number relations for other geometries as well. Now, I am going to do an application, okay, and the application is as follows. You want to have separation of particulates by virtue of the difference in their size. For example, suppose you have and how it is done is using what is called a gravity settling chamber. Okay. Essentially, you have a box, a channel, okay, through which you have flow of a particulate. This is a suspension of this is like a suspension of some particulates like solid particles that are suspended in a fluid, and the flow rate is q. Okay. And the width of the channel is w in this direction, and the height of the channel is h. The gap in which particulate is flowing, it is flowing out in this direction, and the length of the channel is L. Okay. So, let us assume that w is very large. So, we can treat the problem as a 2-dimensional problem. So, you imagine that you have a channel, the height is h and the length is L, and you have a mixture of a gas solid mixture, gas plus tiny solid particulates that flow in, and we want to make sure that when this mixture flows out, we want to separate out the solid from the gas, okay, and that happens by virtue of the gravity which acts in this direction and settling. Okay. But typically in industrial applications, this incoming mixture will have a size distribution of particles. Not all particles will have the same size, you will have particles of varying sizes. Okay. So, but we want to know, So, from settling, from the basic idea of settling, you will imagine that bigger particles will settle sooner compared to smaller particles, because the drag force, sorry, the okay, let's look at the settling velocity. The settling velocity at low Reynolds number is proportional to dp squared. Okay. So, the settling velocity is proportional to dp squared, which is what we derived just now. So, it is higher, particles with higher diameters are going to settle more quickly compared to particles with smaller diameter. So, you can ask the question, suppose I start from here, okay, what is the smallest particle I can capture, okay, in a length L. Suppose you have a settling chamber of some length L and the gap width h. What is the smallest particle that you can capture typically in a settling chamber? Okay. So, let us start with some position A here. Okay. Now, if this particle has to be trapped over a distance L, then it must settle over, it must travel a distance of h within a time wherein it resides in this settling chamber. That residence time is typically the average velocity divided by the length of the, this is typically the residence time of residence. A particle will approximately stay over a time of order u by L, okay, because it has to travel with an average velocity u over a distance L. So, the time the particle spends in this chamber is u by L. Now, within this time, this particle which started out here must reach here as it moves. Okay. So, the particle will do this, the trajectory of the particle will be something like this. Okay. So, if you consider a particle that is bigger than this particle, that is anyway going to settle quickly. If you consider a particle that is smaller, it is not going to be settled, it is not going to settle within the chamber, it is going to fly away with the flow. Okay. So, there is flow in this direction. Okay. So, which is that particle which will exactly start here at A and end here at B, and that particle will be the cutoff diameter which can be separated by this settling chamber. Okay. So, let us look at this analysis. The horizontal velocity of the fluid is simply the average velocity of the flow is simply the volumetric flow rate divided by the area. Area is the cross sectional area of flow, which is width, which is into the board, times the gap thickness h. The residence time of the particle, the time the particle typically spends in the chamber is simply L by V f, which is nothing but W h L by Q. Okay. Now, if the particle falls with a settling velocity, V p, okay, the time it taken to settle over a distance h is simply h divided by V p. This is, let us call it T v. Okay. Now, if you imagine that we wanted a particle which started at A and ends exactly at B. For such a particle, the time of residence, which is the time it spends over a length L, must be exactly equal to the time of settling. So, T h is the residence time velocity time, and it must be equal to the settling time. So, equate the two times, we will have W h L divided by Q is nothing but h divided by V p, or V p is Q divided by W L, as h cancels from both sides. Okay. Now, we have let us say we have small particles, and let us assume that Reynolds number based on particle is small compared to 1. Then we will use the settling velocity that we just derived for such particles, which is g dp squared rho p minus rho divided by 18 eta. We are going to substitute this out here. So, we will get g dp squared rho p minus rho by 18 eta is q divided by W L, or dp is nothing but 18 eta q divided by g W L times rho p minus rho, the whole thing to the power half. Now, this is the smallest diameter typically that can be captured by in the settling tank of this dimension. If q is the volumetric flow rate of the mixture, eta is the viscosity of the liquid, g is acceleration due to gravity, W is the width into the paper, L is the length of the channel, rho p is the density of the particles, and rho is the density of the fluid in which it is moving. Okay. This is the diameter of the smallest particle that typically the diameter of the smallest particle. Now, if a smaller particle, it is in principle possible that a smaller particle than this dp enters the chamber somewhat below A, and it can be captured before B itself, but that is something that we cannot predict with certainty. So, this is typically because the incoming particles will come with a distribution, and each particle will enter the chamber at different vertical locations. So, obviously, there can be smaller particles that can settle in the chamber, but we can make with the following statement with certainty that no particle larger than dp will settle within the chamber. Now, this so far we have been discussing the settling and motion of rigid particles. There is also the case in many chemical engineering applications where you have the motion of drops and bubbles in a liquid. Okay. Now, if you have a drop of some diameter d, okay, and let us say the drop viscosity is mu I and the outside viscosity is mu O, then at low Reynolds numbers based on the drop small compared to 1, okay, the drag coefficient is given by 24 divided by R e times k plus 2 divided by 3 divided by k plus 1, where k is nothing but mu I divided by mu O. Okay. So, it is a ratio of inner fluid viscosity, drop viscosity to the outer viscosity. So, we have two limiting cases. When mu I is very small compared to mu O, you get the motion of an air bubble or a bubble, gas bubble, okay, and you will get C d in that limit. So, when mu I is less than mu naught, k tends to 0. If I put k tends to 0 in this case, I will get 16 by R e. Okay. Now, if mu I is very large compared to mu O, that is k tending to infinity, you get a rigid object, rigid sphere. So, C d becomes 24 by R. Okay. So, it does reduce to the well known cases of it does reduce correctly to the result of 24 by R e when the viscosity of the inner fluid is very large compared to the viscosity of the outer fluid. And we also have a new result that for the motion of a gas bubble, suppose if you have a gas bubble in water, air bubble in water, it is going to rise. What is the terminal rise velocity at low Reynolds numbers? Well, you can use this relation and then find out the terminal rise velocity in a very similar way that we did for terminal settling velocity. Okay. Now, it is not just because of the driving force for settling is typically gravity in many applications, but in some applications you do find the use of centrifugal driving forces, okay, that drive the motion of the particle in a fluid. So, centrifugal forces happen whenever there is a rotation of fluid flow. Okay. So, whenever the direct of particle, so when you have a suspension of a liquid in of solid in liquid, okay, and then if you want to separate these particles based on their sizes or densities, you can use gravity, but gravity you cannot manipulate gravity because it is fixed on the surface of earth. So, if you were to use, if you want to speed up the process, if you want to have more control over the process, you could use centrifugal forces, because these forces also appear as body forces, because this is like motion in an accelerating frame of reference, so rotating frame of reference. So, you have fictitious forces which will act like body forces, and that force is proportional to r omega, the acceleration, centrifugal acceleration is proportional to r times omega squared. So, if you balance the centrifugal acceleration with the drag force, you will get 0 is r omega squared rho p times 1 minus rho divided by rho p. This is the net net force along the direction of the body force, because you have to account for buoyancy, minus the drag force which is opposing this. So, C d rho v squared A p by 2 m. So, the terminal velocity in a centrifugal field is written as omega times square root of 2 r rho p minus rho times m divided by A p rho p C d rho. Okay. So, once you know what C d is, you can actually predict the terminal velocity in a settling of settling even in a centrifugal field. This is often used in if you have a dairy product, a milk is basically an emulsion of droplets of one liquid in another. Suppose you want to remove fat from the milk, okay, and since fat has different density compared to the other constituents of milk, you can centrifuge the milk to separate the fat from the rest of the milk. Okay. So, this is how the process of skimming is done in a milk using centrifuges, and there if you want to design those centrifuges, you have to have a clear cut idea of what is the terminal velocity in order to design the centrifuge, what is the size of the centrifuge you need, and so on. So, such calculations are very useful in the design of these unit operations. So, the next topic that we are going to discuss is related to flow of particulates in a fluid, or we are going to look at the flow of fluid through a bed of particles, which is slightly opposite, different from what we just did. We have so far considered the motion of particles in a fluid. Now, we are going to consider the motion of fluid in a bed of particles. Such beds or such operations are called packed beds in chemical engineering applications. The reason why packed beds are used in many unit operations such as adsorption or even reaction is that the packing offers higher surface area per unit volume for gas liquid contacting. So, typically you may want to conduct an adsorption process in a packed bed, because you want to contact essentially a gas phase with a liquid phase and transfer a species across the interface between gas and liquid, and clearly the amount of the extent, the rate at which the transfer can happen will depend on how much area is available for the transfer, and if you provide a packing that essentially increases the contact area of mass transfer per unit volume of the bed. So, because of this high surface areas, high interfacial area of mass transfer that is available, these are often used in chemical engineering applications. So, the next topic that we are going to do is packed beds. Okay. So, it is going to schematically appear like this. You have a bed of particles, okay, and fluid is going to flow in this interstitial voids or interstitial spaces, okay, between these various particles. Okay. If you want to design a packed bed for a chemical engineering application, okay, you want to know what is the pressure drop to make a fluid flow with some flow rate Q. So, this is the typical design question that comes up in designing packed beds. Okay. So, how are we going to do that? Now, if I were to draw a cartoon of the interstitial spaces, it may look like this. Okay. So, and you can draw several such contours of interstitial spaces through which fluid is going to flow. Okay. So, like this and so on. So, there are going to be gaps through which fluid is going to flow, and so essentially the flow through a packed bed can be thought of as a flow through, okay, a bundle of corrugated tubes. So, you can imagine each path can be like a tube and there are several such paths. Okay. So, there is empty space within the tube and then the rest is all the solid filling. Okay. So, this is the model that we are going to use. A packed bed can be thought of as a bundle of rough and highly tortuous tubes, okay, of some complex cross section, okay, rough tortuous tubes. Okay. Now we are going to assume further, as a further simplification, since this problem is way too complex, okay, we are going to assume that this can be simplified as a bed of uniform circular tubes, okay, such that the surface area of this problem, okay, and the total void volume in this problem will match with that of the real packed bed. Okay. So, that is the only connection that. So, we are going to essentially think of flow through a packed bed as a flow through a bundle of tubes, although in reality these tubes are extremely complex in their cross section and they are very corrugated, but we are going to assume that this is going to look like a straight tube, but we are going to make the connection between the model and reality by saying the following, that assume that the bed has a set of uniform circular channels okay, whose surface area and total void volume match the actual packed bed. Okay. So, this is the only connection we are going to make with the real packed bed. So, let us first look at the real packed bed. Okay, the real packed bed, the total surface area is nothing but of particles is equal to the surface area per particle times the number of particles, total number of particles. Okay. So, that is the total surface area available for the in the real packed bed. Now, the volume fraction of particles is nothing but volume of particles in the bed divided by the total volume of the bed. This is the volume fraction of particles. It is essentially the amount of volume that is occupied by the particles divided by the total volume. This is nothing but the total number of particles times the volume of one particle, single particle, divided by the total bed volume. Okay. Now, the bed porosity is defined by the symbol epsilon, is essentially the void volume divided by total volume. So, the volume fraction of particles becomes 1 over 1 minus epsilon. The volume fraction of particles becomes 1 minus epsilon, because there are only particles and void, only two, it is like a two component system. If voids are occupying volume of epsilon, then this has to occupy, particles have to volume occupy the remaining volume. So, the fraction of that space is 1 minus epsilon. So, the surface to volume ratio of a single particle of a single particle is surface area of a particle divided by volume of a single particle. For a sphere, if the particle is a sphere, okay, SP is nothing but pi dp squared and Vp is nothing but 1 over 6 pi dp cubed. So, SP divided by Vp is 6 by dp for a sphere. Okay. For non-spherical particles, because typically we will definitely have only non-spherical particles in practical applications. Okay. SP by Vp is written as 6 by phi s dp, where phi s is called the sphericity. So, it tells you about deviation from a spherical shape. If phi s is 1 for a spherical shape, because SP by Vp is simply 6 by dp, but for non-spherical particles phi s is greater than 1. So, it is so SP by Vp is denoted by a sphericity parameter. So, you write the so you calculate how is sphericity calculated. You determine SP by Vp for a non-spherical particle and then use this to determine sphericity. It tells you the deviation from the spherical shape. Okay. So, okay. Now, we want to now find what is the equivalent diameter of the tube. Of the tube through which we imagine fluid is flowing inside a packed bed, okay, in this bundle of tubes model. Okay. Now, first thing we will do is to evaluate the surface area of the tubes. Surface area of n parallel tubes of length L. So, here we are assuming that the length of the tube is same as the length of the bed, which is a severe assumption, because in reality the actual length of the flow of the particle actual length of flow of the fluid, since the tube is highly corrugated, should be certainly more than L, but we are now assuming, because we do not know how what is the length of the actual flow path of a fluid inside this corrugated space. So, we are going to assume this the same as the length of the bed itself. So, this is an assumption. Okay. This is nothing but, okay. So, now first we evaluate this and then we will equate this to, this must be equal to the surface volume ratio times the particle volume in the actual bed, in the real packed bed. Okay. So, this is simple to calculate. So, number of tubes times pi DEQ times L, this is surface area of a single tube through which fluid is flowing, and times n, the number of tubes, is equal to, therefore, the surface to volume ratio of a particle which is non-spherical is 6 by phi s dp, okay, times the particle volume in the bed. The particle volume in the bed is nothing but the cross section of the bed times the length of the bed times 1 minus epsilon. This is the empty volume of the bed, but only 1 minus epsilon of this fraction, 1 minus epsilon fraction of this volume is occupied by the particles. So, we have to do that. Okay. So, this is the empty volume of the bed volume. This is particle volume fraction, and this is the surface to volume ratio of a non-spherical particle. If it is a sphere, phi s is 1. Okay. This is one constraint that we have. The second constraint we have is that the void volume in the bed is the same as the total volume of the n channels. So, the void volume is simply S naught times L times epsilon, because this is the empty bed volume, and once you put in particles, this is the void volume, because epsilon is the void volume divided by the total volume. Okay. This is equal to n times pi times L. This is the cross section area of a single tube times its length times the number of such tubes. Okay. So, by equating this to, so D equilibrium D equivalent becomes therefore 2 by 3 phi s. So, if you look at this term, we can get L will cancel out, okay. L cancels out. So, we can get D equivalent in terms of other properties, okay, other quantities. Okay. So, D equivalent becomes 2 by 3 times phi s, and also we have to eliminate for n by using this expression. So, essentially you can write, instead of S naught L times epsilon, you can write this expression out here. Instead of S naught L, you substitute n times 1 by 4 pi d squared L divided by epsilon out here, and then eliminate for D equivalent. So, we will get 2 by 3 phi s dP times epsilon by 1 minus epsilon. Okay. So, this is the equivalent diameter of the various tubes based on the nature of the geometry of the particle dimension, okay, and the porosity of the bed. So, we have already gotten an expression for the equivalent diameter of these tubes through which we imagine fluid is flowing. Okay. Now, the pressure drop depends on the average velocity in the channel, will be a function of the velocity in the channels, in these various channels. Now, the question is which velocity is to be used, because if you consider the bed, so you will have the cross section of the bed as S naught, and the volumetric flow rate that flows is Q. So, this will be what is called the superficial velocity. This is the superficial velocity of the fluid within the bed, because once if you look at the actual velocity, it is likely to be more than the superficial velocity, because the cross section of flow is not actually the entire thing. Okay. There is only some part that is available for the flow. So, it has to be more. Okay. So, how do we do that? How do we find the relation between the superficial velocity and the actual velocity? It is also called the empty tower velocity. If the tower was empty without any particles, then what is the velocity that you would expect in the bed? Okay. So, how do you relate this to? So, Q naught is V naught times S naught. Okay. Now, that is simply equal to n times pi d equivalent squared by 4 times V. Okay. Because this is the volumetric flow rate in these n tubes. Each tube is of dimension of area this cross, and there are n such tubes. This is the volumetric flow rate across the n tubes that we have modeled. Okay. So, V becomes therefore V naught 4 V naught S naught divided by n pi d equivalent squared. Now, there is also this equation, you have this expression that relates n and S naught L E epsilon. So, once you substitute that, but n times pi d equivalent squared by 4 is nothing but S naught times epsilon. So, V bar will become therefore V naught by epsilon. So, we can see that V bar is greater than V naught, because epsilon is always less than 1. Epsilon is the porosity. So, it is always less than 1, and in the limit when epsilon is equal to 1, that is the whole bed is empty, then we will get V equals V naught. Okay. So, now we know what is V in terms of the superficial velocity of the bed divided by the porosity, and we know what is D equivalent. So, we know what is the velocity and the diameter of the pipes. So, we can use the suppose the Reynolds number is low, okay, then we can use the laminar flow relation. So, delta P by L is 32 V bar mu by d squared. So, is 32, V bar is nothing but V naught by epsilon times mu by 1 by, instead of d we will put d equivalent squared, the equivalent diameter, and then substitute the expression for d equivalent. So, you get delta p by L is nothing but 32 V naught by epsilon mu 1 over 1 minus epsilon squared by epsilon squared 4 by 9 phi s squared times d p squared. Okay. Just after substituting the expression for d equivalent that we just derived few minutes back. So, delta p by L becomes, now after doing algebra, the algebra here, you will find that this is nothing but 72 times V naught mu divided by phi s squared d p squared times 1 minus epsilon whole squared by epsilon cubed. Okay. Now, we will stop here and we will continue with this derivation in the next lecture, where we will complete the derivation for pressure drop in a packed bed, both in the laminar regime as well as in the turbulent regime.